is just a continuation of molecularity and order of reaction. Here we have taken a set of chemical reactions written. I have written a set of chemical reactions on the board and their stoichiometric equations and also experimental rate equation. Experimental rate equation, stoichiometric equation of these chemical reactions. This is one more and one more. So many sets, there are many reactions are written. And just looking at that molecularity and this is experimental rate equation, we can understand what are the possible values of the order of reaction. The possible values of the order of reaction. That you understand from the set of reactions. Let us go one by one. Alright, yeah? I am taking this chemical reaction. This is an organic compound. It is also called ester in general. It is a group of ester. It is methyl acetate. It undergoes hydrolysis. It can react with water in presence of mineral acid, HCl or H2SO4 as a catalyst. So water combines with forming that is acid and alcohol. This is acetic acid and methanol. It is known as acid hydrolysis of ester, acid hydrolysis of methyl acetate. This is a stoichiometric equation 1, 1. Always looking at the coefficient of the reactants in the equation, balanced equation. And this is the rate expression for this reaction. Experimentally, you have found that R, rate of the reaction, is equal to rate constant of this reaction into concentration of this into concentration of this. But in this reaction, the concentration exponent is 1. Here, the exponent of this concentration term is 0. That is, the order of reaction with respect to this is 1. The order of reaction with respect to what is 0. It means anything to 0 is 1. So rate of reaction is not depending on the concentration of water. It is depending on the concentration of ester, because in this reaction you are taking the water in large amount, it is in small amount. Usually we carry out the reaction by adding 2 or 3 ml of this, 2 or 3 ml of this into 1 liter of water, large amount, a small amount of acid. So any change in concentration is of not appreciable change. That is why almost remain constant concentration. So it is independent of the concentration of this reactant. So this reaction is first order and bimolecular. It is called as pseudo first order reaction or pseudo unimolecular reaction. Molecularity is 2, order is 1. This is one case. Usually you see all these equations, reactions in many books. This is one case. And the second case is more complicated than this. It is potassium chlorate, a salt. It is dissolved in water. This also takes place in water, aqueous medium, liquid medium. This also liquid medium, water medium. What is the medium in which reaction is taking place? This salt dissolved in water. This salt dissolved in water, ferrous sulfate dissolved in water. This H2SO4 also dissolved in water, sulfuric acid. These are the reactants. The products are KCl plus Fe2SO4 thrice, ferric sulfate, water, KCl, potassium chlorate. Look at this, is quite complicated. The reactants are 3 and molecularity as per the stoichiometric equation is 10. 1 plus 6 plus 3. 10 molecules are involved in this stoichiometric equation. But experimentally, when you find the rate of the reaction depends on the concentration of this to the power of 1 and concentration of this to the power of 1. It is not depending on the concentration of sulfuric acid. So overall order is 2 case here. Look at that, molecularity is 10 and order is 2. It is quite a complex reaction. See, inorganic chemistry. So why I am talking about this? It shows that experimental rate equation need not contain concentration terms of all the reactants. So this example shows that rate of reaction and rate expression need not contain the concentration terms of all the reactant. Here concentration term of water is not there. Here concentration term of sulfuric acid is not there. That is an example for this. That is the kind of order of reaction also we can expect in some chemical reactions. Let us go to the next set of reactions. This is H2 plus Br2 gives rise to 2HBr. Is again a gas phase reaction. Gas. The rate of the reaction is equal to rate constant of the reaction into concentration to the power of 1. Here concentration to the power of 1 by 2. This is all whole numbers. Here 0. Order may be 0 with respect to a reactant. But order is not a whole number, it is a fraction. That is also possible. The order of a reaction with respect to a concentration may be a fraction, or order of reaction may be a fraction overall. Look at this, that is concentration. Actually this concentration exponents of the concentration terms in the rate equation tells what is that tells us that exponent? What is the magnitude of effect of this concentration on the rate of reaction? Higher, more effect on the rate of reaction. Lower, less effect on the rate of reaction. That is why higher the exponent 1, 2. 2 is more effect on the rate of reaction. Here 1 it is less by 1 half. It has less effect on the rate of reaction. So every exponent of the concentration term will tell us that what is the magnitude of the effect of the concentration of that reactant on the rate of reaction. Higher the value, more effect on the rate of reaction. Lower the value, less effect on the rate of reaction. That is why we have fractions 1, 2, 3 are. It depends on the nature of the reactant molecule that we have found by experiment. So that is the importance of order of reaction. So in this rate of reaction, rate constant of this reaction, here molecularity is 2, order is 1 plus 2, 1 plus 1 by 2 equals 3 by 2. So 3 by 2 is again a fraction overall order of reaction. That is our. So like that we have one more expression, that is a decomposition of acetyl, that is acetaldehyde. It is known as acetaldehyde. When it is decomposed, we get methane and carbon monoxide. Decomposed, when it is eaten, we get methane and carbon monoxide. And this rate expression, what is that? It is molecularity is 1. Rate expression, that is experimental rate equation for this reaction is rate of this reaction, rate constant of this reaction, concentration to the power of 3 by 2. More than 1, 1.5 it is. It is not 2, the fraction. More than 1, less than 2. So that is the effect of magnitude of concentration on this rate. What is the effect now? 3 by 2. So he says the fractional order. Similar reaction in this case, it is carbonyl chloride, a gaseous substance. Upon decomposition gives carbon monoxide and chlorine. Again, the rate of the reaction is equal to rate constant into this concentration to the power of 3 by 2. The order of the reaction is again, in this case, 3 by 2, 1.5. We have different fractions, 0.5, 0.5, 0.7, 0.6, anything is possible. 1.5, 2.1 like that. Depending on that is a nature of the reactant. That is always you find by experiment. Experimental evidence says this is the order of the reaction. So this is what he says that this set of examples so says that the order of reaction can be a fraction. Order of a concentration term of the rate expression may be a fraction like this. And go to the next set of reaction. In this case, look at this chemical equation. H2 plus Cl2 gives us to 2HCl in presence of light. It is a photochemical reaction. Photochemical combination of H2 and Cl2 gives us HCl. It is a, of course, free radical mechanism, very fast reaction. When you look at this, in this reaction, the rate of the reaction is not depending on the concentration of hydrogen and also not depending on the concentration of chlorine. That is concentration to the power of 0, concentration to the power of 0. It is 1, it is 1. R is equal to K. So rate of the reaction is equal to its rate constant. Rate of reaction is always constant, no variation. So there is no effect of the concentration of either hydrogen or Cl2. Neither concentration of H2 nor concentration of Cl2 will have effect on the rate of reaction. Nil. So that is what it says, that overall zero order reaction. Zero order with respect to this, with respect to this. Overall order is 0, molecularity is 2. So rate of reaction is equal to rate constant. In this case it happens. Usually rate constant is defined as when the rate of reaction equals K, when the concentration of all the reactants equals 1. And is 1 no? Or equals. Concentration of all the reactant term is equal to 1, rate is equal to rate constant. So that is the definition of rate constant. We shall take details about that rate constant in the later classes. So in all zero order reaction, remember in all zero, this is called zero order reaction. Rate of reaction is equal to the rate constant. So similarly we have two more reactions like this. It is the decomposition of nitrous oxide on the surface of platinum by the effect of heat. Decompose into nitrogen and oxygen is a stoichiometric equation. Rate expression is K into N2O. Independent exponent is 0. So rate is equal to rate constant in this case. Zero order reaction. This also zero order reaction. This is the decomposition of ammonia on any solid surface by the application of high pressure. In very high pressure, by applying very high pressure on the solid surface, this will decompose into this and this. This is exactly a reverse of Haber's process. So the same reverse now, we manufacture ammonia in the Haber's process by using nitrogen and a reverse case. So this ammonia is very important in the manufacture of fertilizers, ammonia fertilizers. So this reverse of this is a zero order reaction. So rate of this reaction is equal to rate constant, is independent of the concentration of ammonia in this case. So this reaction show that there are reactions of zero order. That is n value is 0. In the next set of reaction, so here I am taking this example, dissociation of ozone into oxygen. Ozone is molecule of three oxygen atoms. Oxygen is a molecule of two oxygen atoms, diatomic, triatomic. This is dissociated in presence of UV radiation. So in this case, so this is the stoichiometric equation, molecularity is 2, but when the reaction is examined, rate of this reaction is equal to rate constant into concentration of ozone to the power of 2, but here concentration of oxygen as well. Very important, very rare case. Rate of reaction need not contain concentration of only reactants, it can also contains concentration of product as well. But oxygen is product. The positive or negative way, of course, is minus. So that says that order of reaction in the concentration term need not be fraction 0 plus, it can be negative as well. The concentration term. So this is a very typical example to show that the rate equation can contain the product concentration term as well. as well as exponents need not be positive, it can be negative. But this negative means the rate of reaction actually it is what is that it decreases as the concentration of oxygen increases, is inversely proportional. So as the concentration of oxygen increases, rate of reaction decreases. But here as the concentration of ozone increases, rate of reaction increases. So positive value says that exponential value says that rate increases with the increase in concentration. Negative value indicates that rate decreases with increasing concentration of oxygen. So look at this reaction mechanism is this, of course. O3 plus gives us to O2 plus O free radical. This plus this combines to give 2O2. This is a two steps of reaction, a complex reaction. Molecularity is equal to 2. R equals 2 minus 1 equals 1. It is quite complicated. Pseudo order reaction. And very interesting point is that why I am talking about this reaction. This chemical reaction occurs in the upper atmosphere. This is the most important reaction because in the upper atmosphere all the UV radiations are filtered out, removed by this chemical reaction. These substances absorb. So oxygen, ozone absorb this. How is ozone is formed? Ozone is formed by the action of UV radiation on the oxygen. That is not shown here. First, ozone formation by the action of UV radiation on the oxygen atom. That absorbs what is that one range of frequency of UV radiation. After the ozone is forming, this ozone will absorb this UV radiation of another frequency range. Therefore, you see that range of frequencies wavelength. So as a result of these two formation and decomposition, almost all the UV radiations are filtered out in the upper atmosphere. That is a safe reaction. This is a God gift. UV should not reach the surface of Earth. They are quite dangerous. Living beings cannot survive. And what is that? Multiple diseases and cannot survive for whether plant or animals or microbes. UV should not be exposed for a longer time on any animals or plants, living beings. So this is what this I am showing what is the importance of this. As the concentration of oxygen increases by the action of this, rate of reaction reduces. Not as we expect increase in the ozone concentration. This is the way reason the rate of this reaction, what is that, should decrease when the concentration of oxygen increases by this reaction, because if it is decreased, then there remains a constant amount of ozone for further reaction. Otherwise, so it will have further, that is, what is that, this is the importance of this. This will make some, what is that, not to decompose all the ozone, to remain over there some amount. That is the one. That is a order of the reaction depends on the concentration to the power of -1. This will decrease as the concentration of oxygen increases forward. As the reaction progresses, rate of reaction decreases. There should be there to maintain some constant amount of ozone in the atmosphere. That is the significance of this. So this shows that the rate equation can have negative value as well as the concentration in terms of product as well. That is a significant. That is a typical example for this. And one more like this. One more. The rate of reaction in all these cases, what is that? It is a concentration term of reactant and concentration term of the product as well. But here, in this reaction, it is oxidation of sulfur dioxide. That is sulfur dioxide plus oxygen in presence of nitric oxide catalyst. Sulfur dioxide, gas, homogeneous gas-phase reaction. Here, this acts as a catalyst, neither reactant nor product. It remains still. So the effect, what is that? The presence of this only enhances the rate of reaction, increase the rate of reaction. So this rate of reaction is equal to rate constant into concentration of this to the power of 2. It is independent of concentration of this. but depending on the concentration of catalyst. A typical example showing that rate equation can have the concentration term of catalyst. Very rare cases. Usually it is not independent of concentration of catalyst, but very rarely we see this kind of reaction. So overall order is equal to 2 plus 1, 3. Here 0 order reaction with respect to sulfur dioxide. So one more example is enzyme catalysis. What is enzyme catalysis? So all the biological reactions, whether plants, animal, microbes, macrobes, all the biological reactions take place inside the cell. What the cells they have, many cells are like that. So inside the cell, what is that? Biological reaction take place, and every biological reaction is taking place in presence of enzyme, a particular enzyme. A particular enzyme is highly specific. One reaction can have only enzyme. Enzyme are all protein molecules, giant molecules always. This substrate, this is called as a substrate I call here, this is also reactant. In enzyme reaction, this reactant is called as substrate. Usually this is also a big molecule, macromolecule, of molecular size of medium size. Substrate and this size. In this reaction, what is that? Enzyme combines with substrate reactant. Reason here, it is a big molecule of course, contains lakhs of chemical bonds. Not all chemical bonds taking part in reaction. Only some point on the molecule. Only some chemical bonds on the molecule will take place. What is that? Undergo. What is that? Will take part in the chemical reaction. At that point, what is that? It requires activation because molecule is quite big, cannot be activated. At that point of reaction, it requires activation for reaction. For that activation, it requires what is a molecule like this. This molecule can bind with this because the configuration or conformation structure is like that. Will favor the binding with this at that site. The binding will activate the reaction at that point. Binding. After binding, undergo reaction and gives product. The product molecule after its formation, it is a different conformation, different structure. The structure will not favor the binding of enzyme. Enzyme is separated. So what is taken here is released, product. So after the reaction this separated product changing. So this is the mechanism of enzyme catalysis. Usually all the enzymatic reactions will have this kind of mechanism. Enzyme activity. This enzyme is called as a catalyst in biological reactions. So here the rate of all enzyme catalyzed reaction depends on the concentration of enzyme, depends on the concentration of catalyst. That shows that all biological reactions. Here concentration to the power of 1, concentration to the power of 1. So it is substrate concentration. There are two possibilities. When substrate concentration is very small, it is first order with respect to substrate. When the substrate concentration, this concentration of reactant is very much high in that cell, that is, it is not depending on this. It is depending only on this enzyme concentration. So order is 1. So order is 2 when this concentration is low. Order is 1 when this concentration. But anyway, whether the reactant has lower concentration or higher concentration, rate of reaction depends on the concentration of enzyme. Because these enzymes now release in the cells only when that reaction is required to be done. So when the system is asking for this synthesis, enzymes are automatically released. Same thing that requires enzyme. So enzyme release now, it depends on some concentration is very important. Enzyme concentration. So enzyme concentration plays an important role on the rate of reaction. If there is a very low concentration of enzyme, the rate of reaction is quite decreased to a lower rate, not expected rate. We need expected rate for the synthesis of these molecules, which require to be there. That is why. So rate of reaction depends on the catalyst. So these examples, this is inorganic reaction, this is a biological reaction, shows that order of reaction, that is the rate constant, is rate expression also contains, it is catalyst concentration term in the equation. So these are the example shows that what is that, what are the possible values of the order of reaction and the importance of this order of reaction in studying the chemical reaction, taking overall all the possible values and all the possible significances of the order of reaction.